SieveofEratosthenes is a good case study for advancing to the next level of parallel programming. So this method is invented by the Greek mathematician Eratosthenes in 276-194 BCE. This method actually sieves out the prime numbers from the list of natural numbers.
This time we're going to use a technique called the sieve of Eratosthenes to find out all the prime numbers in between 1 and 100. So let's start the process. First of all, 1 is not a prime number, so get rid of it. 2 is, because it's divisible by itself and 1 only. But all the other multiples of 2, in other words all the other even numbers, can't be prime, so let's get rid of those as well. The next number 3, well, it's not divisible by 2, so it must be a prime number itself. But let's have a look at the multiples of 3. They're not prime numbers, and so we zap them. 5 is the next number, and it must be prime because it's not divisible by anything smaller than itself except 1. Get rid of all the other multiples of 5 though. 7 is a prime number because it's not divisible by anything smaller than itself except 1. Let's look at all the other multiples of 7 in the list and let's get rid of them. Now we have to stop and think. Think about the numbers on the list which haven't yet been knocked out. If they are divisible by a prime number which is larger than 10, then they must also be divisible by a prime number which is smaller than 10, because 10 tens are 100, and you can't have numbers divisible by 2 prime numbers which are both larger than 10. So it follows that every other number on the list is prime, because we've got rid of all the numbers which are divisible by 2, 3, 5 and 7. So all of the numbers which haven't been taken off the list at that stage must also be prime numbers. And we've done it. We've found out a list of all the prime numbers between 1 and 100, and there they are in blue. This technique is called the sieve of Eratosthenes because the ancient Greek mathematician Eratosthenes used this technique. Why is it called a sieve? Well, basically, if you get rid of all the numbers in the list which are not prime numbers, just like letting them fall through the holes of a sieve, then what you're left with in the sieve is just the prime numbers themselves. That's why it's called the sieve of Eratosthenes.
This is the pseudocode for sieve of Eratosthenes. First, we'll create a list of natural numbers from 2 to n, none of which is marked at the start. Set k to 2, the first unmarked number. We will repeat marking all the multiples of k between k square and n. Find the smallest number greater than k which is unmarked. So this will be the new k. This has to be repeated until k square is greater than the value n. After having this pseudocode executed, the final unmarked numbers are all primes. So how to solve this sieve of Eratosthenes parallelly? There are two data decomposition options for partitioning. The first option would be interleaved decomposition, and the second option is block decomposition. We will see each one. In interleaved decomposition, the tasks are assigned to each process in a round robin fashion. That means the process 0 will be responsible for the first task. The second task will be assigned to process 1. Likewise, in a round robin fashion. So here in sieve of Eratosthenes, we start with natural number 2. So you can see that process 0 will be responsible for 2, 2 plus p, 2 plus 2p, where p is the total number of processes. So here the advantage is that in interleaved decomposition, given a particular array index I, it is easy to determine which process controls that index. But here again, the disadvantage is that it leads to load imbalances among the process. In block decomposition, we are going to assign the task to each process, but the task will be containing a block or a set of natural numbers. So we are going to divide the array into p contiguous blocks of equal size. So naturally, if n is a multiple of p, definitely it is going to be a straightforward division where we have n divided by p elements exactly equal for all the processes. But what happens if n is not a multiple of p? Here again, what happens if 100 is divided by 30 or 10 divided by 3? So we are going to take an example here. So here we have total number of elements equal to 13. P is equal to 3. So what we have to do is we have to compute R. What is R? R is n mod P. N is 13, P is 3. So 13 mod 3 will be 1. So if R is equal to 0, that means n is going to be a multiple of P. So no worries there. But if R is greater than 0, we have to assign the floor or the seal of n by P to the first R processes. And P minus R processes will keep the floor of n by P. To simplify it, let's see the example again. So here you can see that the first R process, here R is equal to 1. So the first R process will be sealing it, 13 divided by 3, which is equal to 4 point something. When you seal it, it will get 5 tasks. So the first process will get 5 tasks. And what happens to the P minus R? Here P is equal to 3, 3 minus 1, 2 process. The rest of 2 process, what they get is flooring will be done. 13 divided by 3 floored, which is equal to 4 tasks each. So here you can see that in the example, the first process will get 5 tasks and the second or the rest of the processes will get 4 tasks each. In the example drawn here, you can see that there are 17 elements which are divided among 7 processes. You can see that the first three processes will get 3 each and the rest 4 will get 2 each. What if the 17 elements are divided by among 5 processes? So you can see the first 2 is getting 4 elements each and the rest getting 3 elements. And if it is divided among 3 processes, the first 2 will get 6 processes each and the rest of the process will get 5 tasks. We need to balance the workload here, particularly when n is not a multiple of p. Usually, each process gets either the floor of n by p or the seal of n by p. So what we are going to do is we are going to define some macros where we are going to find the low and high indices given an honor. Or given an honor, we are going to find the index. So we are defining 4 block decomposition macros here. The first one is block low, which is an expression whose value is the first or lowest index controlled by that process. So block high is the macro which expands to an expression whose value is the last or the highest index controlled by that process. Block size evaluates the number of processes controlled by that process ID. And block honors evaluates the rank of the process controlling that particular element of that array. So these are the 4 macros defined for our SieveofEratosthenes program. Here you need to know the difference between local and global indices. When you say local, it is local to that process. When a task is 0 and it is local, that means it is the first task of that particular process. When the global indicates that it is 5, that means it is the 5th task of the whole communicator. So that is the difference between local and global indices. You can see that here, this particular task is having 0 local index, but its global index is 10. So when we are going to implement the SieveofEratosthenes using MPI program, what we are going to do is we are going to use the collective communication routine broadcasting here, MPI bcast. So here what the process 0 is actually broadcasting a single integer k to all other process. And this is the code. We are using the reduction operation here. So this is the improved version of SieveofEratosthenes program. So this is obtained from Wes Kendall's GitHub. So let's build this solution here. So we don't have any errors. So let's try running it from the command prompt. So we'll go to the appropriate directory. Okay, now let's run it. MPI exec. We'll start with 3 process and okay, now we have to give the command line argument. Let's say 1000. So we are going to find out the number of prime numbers below 1000. So it says that 168 primes are there under 1000 and the total elapsed time is also given here. So this is the end of the session for SieveofEratosthenes, a case study for MPI programming.